All right, welcome everyone to another Astronomy on Tap live stream. Thank you all for coming out. My name is Michael Roderick, and together with Arvind Gupta and Jacob Lund, we run the Astronomy on Tap State College chapter. So tonight we have two awesome talks, one by a former colleague and friend, Corey Gray, he's still a friend, just a former colleague, Corey Gray from LIGO, Penn State graduate Evan Sneed. We're going to be talking about translating LIGO discoveries into Blackfoot and biosignatures and text signatures in planetary atmospheres. So if this is your first time tuning in, format is we're going to do a brief introduction right here. Jacob is going to tell us how to make our astronomy-themed drink. Then we'll have our first talk, which is going to be Corey, followed by trivia with Arvind, astronomy in the news with Jacob, our last talk with Evan, and then find out the trivia answers again with Arvind. So I think I can go ahead and hand it off to Jacob, and he is going to show us how to make our astronomy-themed cocktail. Go ahead, Jacob.
All right, thanks, Michael. So tonight we're going to be making a space-themed twist on the classic Long Island iced tea drink. And this is an idea that came up and then later realized that Long Island has a lot of things in it that I didn't know had in it. So if you found all the ingredients, great. There's also a Long Island iced tea mix that you can get that has the combination of all of these things. So we're going to be using some white rum, some tequila, vodka, triple sec, and then also some gin. But it's a pretty straightforward recipe because it's going to be using equal amounts of everything. And we're going to be using about 3/4 of a shot. I'm just going to eyeball it. This is, or 3/4 of an ounce, sorry. I'm just going to eyeball it. This is a 1 ounce measuring device. So if you have your own Long Island iced tea mix, you'll probably want about 3 to 4, maybe 3.5 shots worth of that. And then you'll combine it with the simple syrup and then the rest of the ingredients. But I'm going to go ahead and start pouring all of these ingredients. So we're going to start with the gin, and again, about 3/4 ounces. And you get to watch me pour a lot of things today. And 3/4 of an ounce. Put my lids back on. Another 3/4 ounce. Ooh, that one got a little heavy. And then lastly, the white rum. I don't know if you can use dark rum. I think maybe it's just for the coloring. To be honest, I don't know the difference between white and dark rum. I just went by recipes online. All right, so there were our alcohols, and then we're going to throw in some simple syrup. Again, about 3/4 of an ounce. All right, so we've got all of that. And now you're going to just give it a good stir, mix it all up. There's a lot of different liquids in there. And then I like to add the ice now. So you want a good amount of ice because this isn't actually going to be all that much liquid. And, it's a decent amount of alcohol, so you want to really sip on this, keep it cool for a long time so that you can really sip on it. One more, sure. All right, and then out of the way. To finish off a Long Island iced tea, you would top it with some Coke. I don't have real amounts here because all the recipes just say top off with Coke, which is really imprecise. So I'm just going to do the same thing. But I sort of go by color. You know, you kind of get a color that you like. I think I'm going to fill it up to about here. That looks all right. And so you top it with Coke. Now, normally in a Long Island iced tea, you'd maybe add a squeeze of lemon, and I do have some lemon here. But actually, we're going to include some Leinenkugel Summer Shandy. And this is what is giving us our space-themed twist for the night, because with our Leinenkugel Summer Shandy, we're going to be making an LSST. And for those of you who aren't familiar, LSST is the legacy space or legacy survey of space and time that's taking place or going to take place at the Vera Rubin Observatory down in Chile, and is going to be covering basically the entire southern sky, imaging it once every few nights. And so that's our inspiration for this drink tonight. And one little fun fact here with LSST, because it's taking images of the sky every night, it's getting a lot of data. So there's going to be a lot of data generated from these images, something like 8 terabytes per night for images. And so just like our drink tonight, LSST really packs a punch. And I'm going to top it off actually with a little lemon wedge here and a squeeze, just to give it a little more flavor. And there we have it, our LSST. Cheers, Michael. Yep. I do have an apron. I could wear that next time. I'll keep that in mind.
Hey, Michael, testing. Can you hear me? Okay.
Oh man, I just had myself muted, so I just want to say again, this is Corey Gray. Sorry everybody that you couldn't hear me. Corey Gray from LIGO Hanford Observatory, here to tell us about translating LIGO discovery to Blackfoot language. All right, go ahead, Corey.
Am I unmuted? And then
You
we
can
have
go ahead and talk.
And are we sharing the screen? Is everything? Do you see my first slide?
I do not. I see your desktop background, which you really need to clean up because there's a lot of screenshots there.
Okay, let me stop and try that again. Like I said, I'm pretty in this work at home situation. I'm pretty new with doing virtual talks. So let me try this again. Oh, okay. Yep, I know what I did wrong. Okay. You are all my guinea pigs for doing virtual lessons. Okay, so now do you see a different desktop?
I do, yes. And it says Corey's talk.
Okay, and I'm going to put that in presentation mode. And is that taking the full screen now?
Yep, go ahead.
Okay, so I'm going to start my stopwatch. Okay, so thank you, everybody. This is my first time doing an astronomy on tap. My talk is mainly going to focus on a specific story related to the work that I do, and just a personal story about me. So my big ask is that I won't cover a lot of the science of LIGO and a lot of the detections because I just have 20 minutes. So I want to, I have a lot of information here. So I'm going to try to pack in as much as I can. But with that, I'm going to try to squeeze in some cool things that you might not get to see in typical LIGO talks. And so they'll be kind of peppered throughout. And so this talk will be covering a bit of history and then about my tribe. So you'll find out a little bit about that, but you will learn a little bit about gravitational waves and linguistics and indigenous languages. My mom is the real expert. So I'm going to be trying to do the best I can without her here explaining the work that she did for us. So the title of my talk is Blackfoot Poetry of Einstein. And I just have a couple notes here. Indigenous Peoples Day is less than 2 weeks away, October 12th. And then there's Native American Heritage Month, which is the month of November. And then as we all know, November 3rd is the election. So it's very important to exercise your rights to vote and be a part of democracy, and be sure to vote. Okay. And since Michael invited me here, I had to share this picture of when he was, when we worked together. We were both detector operators. And this is just evidence of him and his karaoke singing skills back in the day. I can't remember the year. It must be 2011, 2012 or something.
You can see how grad school will age you.
You were such a kid back then. You look so young. Okay, so I'm Blackfoot, and the Blackfoot Confederacy consists of 4 bands of Blackfoot tribes. And so my tribe is the Northern Blackfoot, or Siksika Nation, and this image that is here is a picture of our reserve or reservation or Siksika Nation. And what you're seeing is just the valley that it runs through the reserve, and the Bow River is the river that you're seeing there, and that's 60 miles downriver from Calgary. Here's a map that's covering just some of the Indigenous peoples of that area of Canada, Western Canada, and the United States. So can you see my mouse when I move it around on the image?
Yeah, you're good. We can see that.
Okay, good. So I'm just going to point out the 4 bands of Blackfoot. So there's the Blackfeet Reservation. That has the very big reservation in northwestern Montana. It's right next to Glacier National Park. So that's the biggest band of Blackfoot. And then there's the Kainai and the Piikani, and then the Siksika. And so the Siksika is where my family's from, and I took that picture of the river right about there. The green is kind of designating what our original territory was. This was before the Queen forced our people to live on these smaller plots of land, or these reserves. So that was the original area of the Blackfoot people. We were known as a Plains tribe. We were also known as a warrior tribe. We fought a lot with the Cree. They used to be our sworn enemies, but actually a lot of Cree people are my friends now. So. But yeah, this is just an idea of how much our land was reduced, or our territory was reduced by the Queen. And that's a similar story in the United States as well. So this is a picture of my family. This is my mother, Sharon Yellowfly, my uncle, Sherman, and then these are my grandparents, Percy Yellowfly and Cecile Yellowfly. Her maiden name is Slay. Percy was a chief for our tribe for, I think, 1 or 2 terms, I think in the 60s or 70s back in the day. I just love these old-timey photos. I always share them when I give talks. This particular photo is a recent one that my mom shared with me. It's one that she took. This is at the Calgary Stampede back in the 60s, I think. This is my great-grandfather, Alphonse Slay, and this is a TP that was given to him by Chief One Gun, who is also a relative or in our family. And I love this image because of the teepee here. This is a teepee known as a star teepee. And so the colors of it is white circles with the red background. And so that's a star teepee that my family had. And so one of the things I like to do is just really say that science and astronomy, engineering, and a lot of these topics are part of Indigenous culture. And I try to say that to, especially to Indigenous youth when I'm giving talks on reservations or Indigenous communities. Additionally, so I mean, astronomy is part of our stories. It's on our TP designs. We recorded, there's records of astronomical events being recorded by our tribe and many tribes, such as meteor showers and stuff like that. And they're documented on, like, for our tribe, it was buffalo hides, and we call those a winter count. And you could see when the stars fell as something that was documented like many years ago. And then this is something I learned about more recently personally, and this is called a medicine wheel. This is the Majorville medicine wheel, which is also on Blackfoot territory. And I took this picture when I went to go find it about 2 years ago. And this instrument is piles of rocks that are arranged in a way. And the thought is that they were used to mark the seasons and monitor the sun in the sky as well. because yeah, there's another ceremony that's a big plains ceremony called a Sundance, and so that's what the idea is here. That this instrument on the plains help to look at the sky. It's called a medicine wheel, and it's over 5,000 years old. So it's older than Stonehenge. It's about the same latitude as Stonehenge too, which is kind of interesting. A similar instrument on not the plains, but the desert is this one. This is about 20 minutes from my house right now. This is where I work. So this is the LIGO Hanford Observatory. And this is just a picture I took from a friend who was, he rented a plane and I got to hop in and take some photos. So this is a photo of the detector. My title slide was a picture of the Y arm at sunrise during or towards the end of a graveyard shift. And I took that picture right about here, looking back towards the corner station right there. So that's where that picture was. And so we've been collecting data for observing run 303 from April of 2019. And we were supposed to go till April of this year, but we ended a few weeks early because of the COVID situation. So I've not been at work for many of those months up until this last month. So here's a picture of me. Actually, this was last week. I had some work to do in at the lab. And so we're slowly ramping up activities right now. So right now we're at a state where we are doing an upgrade for the detector. Lots of tumbleweeds here too, as you can see. What else was I going to show? Okay, so this is me over the X arm. So this is me over the other arm. And so this bridge, there's a bridge right here. So that's where that photo was, and it's looking back this way. And then one thing I like to do is we could pretend we're photons traveling in those 4-kilometer arms. And here's a cool little video that yeah, you can see it. A lot of tumbleweeds. Here we come up on 2 kilometers. This is going to be the liquid nitrogen truck that we're going to see at the mid station. That's it right there, mid X. And now we're at 3 kilometers now. And here's the 4-kilometer, this is the end station, end X, right there. So yeah, I took that last April. And this was a move that just happened just a couple of days ago. We're doing, in this new upgrade, we're moving chambers around. This chamber, I think we're shipping to Louisiana. That's where the other detector is. And it's just another time lapse that I have of us craning it. This thing weighs just under 10,000 pounds. So it's kind of a cool thing just to watch. So this is very quick. I think there's about 3 or 4 chambers that will be moving around. And inside of those vacuum chambers, we would have optics tables that are seismically isolated, all types of mirrors, detectors, etc. Depends on where the chambers are located. Okay, so what are we known for? What's the big discovery that we had? So the big discovery we had was the one that was the first direct detection of gravitational waves on September 14th, 2015. This is what we saw. This is what the detector in Louisiana saw at 4:50 in the morning that morning. And then at the observatory I work at, 2 hours and 50 minutes after my shift, this is what the detector saw in Washington. And you could take both of these plots and put them over them. Yeah, so the signal, it was Louisiana saw it first. We saw it 7 milliseconds later. They always remind us of that. But one thing is that when you shift the time and line them up with each other, you can see that they have the same plot on them. And so what we're seeing here is just the last fraction of a second of the dance between 2 black holes, 1 billion light years away, right before they merge and form a single black hole. And then this is the burst of gravitational waves that pass right through the Earth that we saw there. So yeah, this is that first detection. It happened at 2:50 in the morning here. I like showing this email because this is mentioned in some magazines, but yeah, I went and looked in my emails and I found it. So this is the one when the first human saw this trigger that was automatically sent to him from our searching tools. And you can see this was at 3:55 in the morning that morning. Yeah. So that was September, and then up until we announced, which was in February, we had to be totally quiet. We were under embargo. We couldn't say anything about this huge discovery. And there's reasons for that. I mean, we didn't want to announce ahead of time. We wanted to make sure that we really saw this event. We wanted to write a paper about it. And then once we were pretty much ready to go, then a group of us, the outreach group of us, worked on how we would announce it. And so the topic of a press release came up. And the LIGO scientific collaboration, which has 1,000+ people around the world, and so there's a lot of languages that we can translate that press release into. And so that came up in a talk. And so in that talk, in that meeting, I didn't bring it up. So it was after the meeting, I talked to the head of our outreach group, and this is the email I sent her. Her name's Dr. Joey Key. She's at UW Bothell. And yeah, so the whole thing is, it's a little political because my mom would have to see this private document that was top secret up until we announced. And Joey was totally excited about it and totally approved it. So that is, you can see the dates here. This is February 3rd, 2016. And then a little over a week later, that's when we made the announcement. And this is at the National Press, this is at the Press Club in Washington, DC. So if you want to see a really cool video, check out that press conference. It's pretty amazing. And just all of the speakers did awesome. I watch it every month or two. So that's the announcement. All of our documentation went online that morning. So all of the press releases were released. And then on the webpage for LIGO, you could see that there's a shout out to Siksika. So that on that, if you click that link, you get a PDF of the translation that my mother made. And here is that translation interweaved with English. So I made, my mom did all the hard work. I just did the grunt work. So this is me just making a text document for the translation that she made. And I think that, and then this article were both in Indian Country Today. And then there's another article in this magazine here. You can see I'm wearing a gravitation, a detection tie from that first detection. This is from the Yakima Reservation, which is right near where I live here in Washington State. And then here's my tribe's paper, where they also shared the news about what my mom did for us. And then this is my mom and I at a conference, I think 2016. Okay, so I'm going to go back a little bit and just kind of share the history of our language and just my family and our people. This is an old picture, and this is my mom here. And then here's another picture of my grandparents. And so the sad history that is a part of this whole thing, and a reason why me or my siblings don't know our language, is because of the federal policies of the Canadian and the US governments to kind of deal with Native Americans or indigenous peoples. One way they did it, I mean, there's several ways. There's a termination policy or extermination policy. Termination, where they tried to terminate tribes off the books. And then there's assimilation. So this is one part of it that my mom had to suffer through, is assimilation. And so one way they did this was by taking the kids away from parents and forcing them to go to boarding school. So this is the boarding school that my mom was forced to go to as a kid. And this boarding school was on our reserve, which is, I guess that was a unique thing. A lot of other tribes were bused or trained to other boarding schools far away from home. So my mom was actually near family and on our reserve. This is a picture of my mom at the remains of that boarding school. That one was torn down. There's a second one that's still there, and that's being used as a community college. So yeah, so my mom survived that. She's a residential school survivor, boarding school survivor, and they weren't able to keep her from the language. I mean, they had a secret society where they kept the language alive through the just amongst each other, amongst all the kids. And so back to the translation that my mom did. This is a picture of my mom and I giving a talk at an Indigenous language symposium. That was a couple years ago. That was my first time ever getting to do a talk with my mom. And what is cool about this is this was in Lethbridge, Alberta, and that's Blackfoot territory. So there's a lot of Blackfoot speakers there. And especially a lot of people from our tribe, the Siksika Board of Ed were here. And they had no idea about LIGO and what my mom did for us and how she connected Einstein with our language. Here's my mom. Okay. And then I also recorded my mom. I sat her down and I recorded the translation of that first detection. And it's on YouTube. So if you ever want to check that out, you can check that out. And I'm just going to go through just very quickly just some of the words. She separates them into a few categories. So there's words that we already have. And so my mom calls these traditional. So these are the words and the translations. Other ones are called direct. And so it's basically taking other words and putting them together. I mean, there's a word for black and there's a word for whole, and she puts those two Blackfoot words together to make that. And that's why she has eggplant. It's a similar thing, egg and plant, and you put the words together to make one Blackfoot word. But then there's words that aren't in Blackfoot. So there's general theory of relativity. And so she calls this having literary license. And this is where she just comes up with an idea, I guess, in English, and then thinks of Blackfoot words to explain that idea she came up with. And so that's the literary license category. And then conceptual. And then this is where she's, I would work with her and tell her what these words mean in English. And then she would take that and then think of a way to say it in Blackfoot. And so it's always funny. I love looking at these new words and just seeing how she makes these words. And you can see the Blackfoot words are really long as well. Man, it's already 17 minutes. Okay. Still plugging along. I was gonna play this video. So my mom's done 10 documents for us so far. 7 were press releases for detections. And then this year she's switched to science summaries, which are a little more technical, but they're also prettier because there's images in them. This is gonna have music that I put in. This is just a numerical simulation and I add music to it just because it's fun. But this is for GW 1904-12. I'm gonna mute this because it's a little loud. So that the number is the date of when this candidate happened. This is now a detection, so because it has GW, it's a detection. And so I'm not going to explain too much about this because I want to focus on my mom's work. So here's the science summary for that one. I have the English version here, and then that this was announced, GW 1904-12. And then these are some of the new words that came from that one. I don't know which ones I think are my favorite. I like spectrogram. I like how she came up with that one. What else? Following Yoda speak. That's the other thing. The English parts she says are kind of in Yoda speak, and so that's the way the words are kind of made in Blackfoot. And then at the end of the science summaries, I put this little blurb in that's a pronunciation guide that she made up because she made this. She made a Blackfoot dictionary for us, her kids. So she did this all on her own. She has a background in anthropology and linguistics. And so she did that all on her own for us. And so there's curriculum that's out there now in schools on our reserve and in Montana. And so the translations will look a little bit different because my mom's using different symbols for different sounds. So I like to put this in there just so people know that. And so I'm gonna zip through, and then here's another science summary. All of these videos and the documents I'm showing are all online, so I could point you to links anytime. And so this is GW 1908-14. This was the unique one because we had one object that was the mystery object. It's either the heaviest neutron star or the lightest black hole. So that was another, that's why this one's unique. And here's a painting of it, and then also the science summary my mom did for that one. And then here's the most recent announcement we had. I'm just gonna mute this, just so you can see a few cycles on this. These are all on YouTube. This was made by the Max Planck Institute, and I forgot the other collaboration. It's something extreme space-time, simulations of extreme space-time. So this was the one with the 2 largest black holes that we've seen merge into a big black hole. And this is just I think within a month that we announced this one. And so here are the 2 science summaries for that. I'm gonna try to zip through this, Michael. I know I'm over 21 right now. I'm almost at the end. Other things, this story has, okay. This story has mainly been, mainly it didn't get a lot of attention, but it wasn't until someone from NPR happened to hear about it. And so, yeah, so one day, I think it was in the early 2019, Nell Greenfield Boyce called me up one day and asked about the story that my mom did. And so she wanted us to share that on NPR. And so I'm not going to play it, but you can look that up online. And I just love it because you get to hear Blackfoot, you get to hear Siksika, you get to hear my mom speaking as well as me. But you get to hear that over the airwaves. So tons of people got to hear that. So that's why I love that. And there's also an Atlas Obscura article similarly that was also came out around the same time. And so now I'm just going to share just a few things, just kind of fun stuff at the end. Because the other thing that that first detection, the Nobel Prize was awarded to the founders of LIGO. When I heard that they were going to get that Nobel Prize, I knew that no matter what, I would take vacation time, pay my own way, and go to Stockholm and tailgate outside of the Opera House where they got their medals. So that's Kip Thorne, Ray Weiss, Kip Thorne, and Barry Barish. And so this is in the Nobel Museum. That tattoo's mine. And so I had to get a picture with the little display or whatever, the display that they had in the museum there. So this was us outside the theater. And of course, my family wanted to join me. So my family all came with me and we went to Stockholm. These are my siblings. Those aren't the real Nobel medals. Those are actually chocolate replicas. The real ones are about this big, heavier, obviously. Ray gave each observatory a replica. So you can go take a selfie with one when COVID goes away. So you could come visit the observatories in Louisiana and Washington and take a selfie with the Nobel medal. Thanks, Ray. And you can see I dressed up for the occasion, so I wore my tuxedo shirt. Another thing is I just love sharing with underrepresented groups and Indigenous people. This was a keynote that I gave, like my first time really giving a keynote, and this was in November 2015 at Humboldt State University, where I went to school. And I could not say anything to these kiddos. I had this big story that I could have told them, but I could not tell them. That's my poker face right there. And then this is just different reservations I give talks at. That was Hoopa in California. This is the Nez Perce in Idaho. This is I was a mentor for a student on the Yakima Res nearby. And then this one is like one of the first ones I did in 2004 on the Flathead Res. And I'm showing that because of revisiting this place just a couple weeks ago. The window there looks out onto Flathead Lake, which is a beautifully clear blue-green lake. And I was there just 2 weeks ago because I built a kayak. And that window right there is that window. That's the same window. And that's me with the new kayak that I built, which is indigenous technology. It's from the Inuit people of Greenland in Canada and Alaska. In the news, I have to show this. This was at the beginning of the year. This is Tumblegeddon, where there's a huge windstorm here. And we had tons of tumbleweeds that were 10, 20 feet high. And yeah, they're tumbleweeds are our nemesis. I'm gonna say, yeah, so this is my friend who, he's Indigenous, so we went to college together. He made this comic called Soldiers Unknown about his veterans from his tribe. And the illustrator did a conceptual thing of my mom. And so you could see that's my mom, that's Einstein, and I'm supposing that's supposed to be me. So this is just a possible idea for a comic in the future. This is a comic from APS called Spectra. She's a superhero who's specializes with lasers. And so me and this is Nutsini, actually. She's the one who's on shift for that detection, the first detection. And then just Indigenous representation, I'd like to always share that as well. This is me with John Harrington, who's the first Native American astronaut. And then Ron So, he's a grad student at Caltech, who is he's part of LIGO as well. And then this is a session of Indigenous physicists at the Society for Advancement of Chicanos and Native Americans in Science. That's SACNAS. That was a few years ago, yeah. And then here are two Blackfoot astronomers. So this is me and Rob Cardinal. He's famous for identifying a few comets, and he named a few with Blackfoot words. And I'm going to skip through this. This is just me and my mom talking about Hidden Figures, which is a good movie and book. And then I like to share just my social media at the end. So Instagram. I became more into social media with the announcement, just because, I mean, just to share the science of LIGO and the detections. I got more adept at that, I guess. And so one thing I'll end with, oh, this is different. Okay, I'm gonna zip right through these because I like to end with this. So this is just some clips, short clips from my mom's YouTube video.
Mostes LIGO, ita pohku, was Udaspumuk Mixisk National Science Foundation, NSF, ki Mixisk Caltech, ki MIT, Anixkai, Utquinipua, ki Apostutsimia, ki Otuskia, Otwitsikatumia.
So that's just a random section or random clip. This is the end of the talk.
LIGO, Neskskatsimia. Son of a biscuit.
That always gets the biggest rise when I do talks in front of people because, and she didn't say the B word, she said biscuit, son of a biscuit. Here's a blooper.
What made you laugh?
I got the giggles. Okay, I got it.
Okay, Michael, sorry, I ran a little long. So that covers all of my talk.
Awesome. Thank you for giving that talk, Corey.
Yes, of course.
I always forget to ask this beforehand, but again, if people that are watching, if you have any questions, please put them into the chat, type them in, and we can go ahead and ask Corey. So, really curious, how long did it take her to do all these translations, to come up with these new words, to translate that initial LIGO discovery into Blackfoot?
Yeah, you saw the dates there. So it was the 3rd is when I emailed it to her, and she's not savvy with electronics. She doesn't have email, so her husband would have to go down the hill from where they live and get the email from me and then print it out and then give it to her. So from the 3rd of February to the 11th is what she had. That's the amount of time for that first detection. And she had a lot of help from other family. So she'd be phoning family up in Canada. And then she has a lot of recordings of my grandparents or her parents. So that's all of the resources she had. Contrast that, a week and a half to 2 weeks to GW 170817, which was the binary neutron star detection. That one was a lot different, because we had tons of astronomers who also wanted to share that announcement about that huge detection that was seen with gravitational waves and light. So with that one, I think her turnaround was something like, was it a day? I think she did an all-nighter for that one because it was just because the press release was, everything was accelerated for that one. We didn't have 5 months, it was like 2 months. And we had the press release like a night or two before the press conference. So everything was accelerated. But yeah, it's usually a few days to a couple weeks that she takes for translations.
So you made your mom pull an all-nighter. Jeez.
I know. She's my hero. I mean, I'm proud of her, totally.
So I particularly love the term for scientist was all-encompassing smart person. That's amazing. I'm kind of surprised that there was no word for scientist already in the language. Is there like any word for astronomer or like physicist, or would it fall under the same kind of term?
I think it would be the same term because my mom, when she's making her dictionary years ago when I was in college, I remember she would just interview my grandparents. And that was probably a question that came up, like, what's the word for a scientist? And so the one who came up with that is my grandpa, Percy. And so he's the one who came up with all-encompassing smart person. Yeah.
Could they just like make it Corey Gray? Corey Gray means like all-encompassing smart person.
Oh, I was going to say Michael. We should call him Michael, Dr. Roderick.
I appreciate it, Corey. All right, so we got a question here from Aria the Gray, who I guessing may be related to you. What do you have planned for the future? So kind of a broad question, but what is your plan, I guess, for the future for LIGO, or I guess for continuing on these translations? Are you going to take over at some point, or is your mom going to
Oh,
continue doing
that would
these?
be awesome. I think Ari, that is my sister, and she got to hear you karaoke as well. So
Oh
she was out there that same night. I think, and if anybody's going to learn the language, it would be my sister Ari. I think she's the one who's actually doing more work to try to learn it. Me, it's just I don't have time. That's the whole thing. It's a cop out, but it's just I'm always busy, and so it's hard. I distract myself with many things. I mean, I'm always hiking or building boats, and so I should be focusing on. I just wish I had more time. But yeah, so mainly going out and working at the lab, and then we hope to go back online for observing run 4 probably in the next year and a half to collect data again.
Okay. Have there been any other scientific or astronomy discoveries that have been translated by your mom or by other indigenous people?
As far as I know, I'm not aware, but one interesting thing that's come from just giving talks like this and sharing it with other people is that other people are putting it on their radar. There is another UW alumni like you, who recently got his PhD in gravity. I forgot what his thesis was in, but he's Ho Chunk, and after coming to one of my talks, he translated his abstract for his thesis into Ho Chunk. And so I think that's awesome. His name's John Lee, Dr. John Lee.
Nice. And another question from the audience: what advice would you give curious young minds wanting to pursue a life in science?
I think it starts with just basic building blocks. I mean, the classes you took in elementary school, basic math and high school, up to high school, all those things are important. I think that's one thing. And then it's just having the passion, and interest are the other thing that will help you get through it. Because there's going to be tons of times where it can be draining, it can be stressful and hard to find where you want to go or what's the next move. But as long as you have that energy and it's still something that you love, I think that's what helps you. It's at least helped me get through some of the tough times. So just find something that you're interested in, whatever that topic is or research is, and then I think that helps a lot to propel you through. And then just bringing yourself to your work as well. I mean, that's what I do. That's what this whole talk was, just bringing my whole self to my work. I mean, that's what I try to do. Even before the detections, I would always try to be as creative as I could to make the science interesting and fun for audiences. So yeah, there's so many ways to go there, but I hope that kind of helps.
Okay. And do you know if another question here from the audience, has the number of people speaking Blackfoot increased or decreased in the recent years? Do you know how that has changed?
The whole reason why my mom did this when she was a kid, so when she was 26, was because she was saying that people her age were not, or the younger people back then weren't speaking. But what the whole thing about this is that that's been changing. So with tribes across Canada and the United States, there a lot of indigenous communities have that curriculum, and they're teaching kids, and so that it's in K through 12, and so that's where it's starting to change. And so you're seeing these younger ones who are growing up in it, and so that's where I think it's going to get better. And then there's people like my sister who's just doing it like guerrilla style on her own too.
Awesome. All right, and then lastly, I know you showed a photo, but can we ask to see the tattoo in real life?
Of course, yeah. So on that night, or most of the time, the detectors look like this. So it looks like just random white noise. And then on that morning, this is what we saw on both detections as that gravitational wave just passed at the speed of light right through the Earth. The only thing different on that morning is that both of our detectors were vibrated by those two black holes on the other side of the universe. And I got this in Puerto Rico, and I got it on Pi Day, or Einstein's birthday, with my sister. We both got ink on the same day, like in San Juan.
Awesome. Thank you so much, Corey. Really appreciate you coming out here to give us this talk. Thank you very much.
Oh, of course. Thank you, Michael. It was so fun. Thank you for the invite.
Sure. All right. Well, I think we are ready to do our trivia. So I'm going to hand this off to Arvind Gupta. He's going to take over for trivia. And I have the link to the Google form for trivia, so I'm going to take that and post it in the chat. So if you'd like to play trivia, go ahead and follow the link in the chat there, and I'll take you to that Google form. So go ahead, Arvind.
Okay, thanks, Michael. I should be sharing it now. Can you all see that?
Yeah, you're good.
Cool. All right. So tonight's trivia round is based on comparison. I'll explain what that is in a second, but first, for the rules, for those of you who are tuning in for the first time, what we do is I'll give you a set of 15 questions. I'll go through them one at a time. They are always themed. So this month's theme, sorry, is comparison. I'm going to be comparing two different things, and I'll ask you which one of them is hotter or takes a longer time or is larger or things like that. And that's what all these kind of symbols are denoting. And so I'll ask a series of 15 questions following that theme. And you guys will submit your answers through this Google form here. And then the winner, which will be the team that gets the most answers correct, will be contacted later this week about receiving prizes. So the first question of the trivia, though, is asking for a team name. And if there's a tie at the top, so if two teams tie with the highest score, I will decide which team wins that tiebreaker based on who has the most creative astronomy themed name. So if you think you're doing really well, you might want to think hard about having a nice fun name for me. The prizes that we have are an Astronomy on Tap magnet, a bottle opener courtesy of the Central Pennsylvania Observers, an Astronomy on Tap beer koozie, and some nice space themed masks that were hand sewn by our friend Macy. Thank you, Macy, for helping us out with those. So I'll start off with a quick example of what this trivia is going to look like. The question here is, which planet has more water? Is it Earth or Mars? I actually made this trivia before the fun news about Mars came out today. So there's actually an article published today stating that some researchers found that there is actually a substantially more subsurface water on Mars than they thought there had been previously. But regardless of that, the answer still is Earth. Earth still has much more water than Mars. So yeah, just answer whether the first or second thing has more of whatever I'm asking about, and you should be able to get through the trivia. So question one, which is more massive, a Bok globule or Gargantua? And Gargantua here is the black hole that was featured in the movie Interstellar. It was the central star around which all the planets were orbiting in the new system that they were trying to get to continue life on Earth after they couldn't grow crops on Earth anymore. And a Bok globule is, I think, a dark cloud of gas that's collapsing to form stars. Sorry, Kevin, if I forgot what I learned in your class a few years ago. Question number two. I'm asking whether in outer space there are more naked eye stars or Starlink satellites. And here I'm defining naked eye stars as stars that a person with 20/20 vision can see on a perfectly clear dark night with no light pollution, but also without something like binoculars or telescopes, something you can just see with your eyes. And so are there more of those stars out in space? Or are there more Starlink satellites orbiting the Earth right now? Number three, have more people walked on the surface of the moon or served as the administrator of NASA? And I think the first one is a little self-explanatory. It's pretty easy to know whether or not a number of people have walked on the surface of the moon. But for the second one, I'm only defining this as people that have officially been instated and served a significant term as the NASA administrator, and not people that filled in for a day or a month or something because somebody was sick or had just passed away. Number four, is it hotter on the surface of Venus or on the exterior of a spacecraft while it's re-entering the Earth's atmosphere? And this is an artist rendition of the Apollo 11 module coming back in after the moon landing. Number 5, are Saturn's rings more massive, or was the asteroid that killed the dinosaurs more massive? So Saturn's rings, this is the total mass of all of the material that makes up the rings of Saturn. And the KPG, or Chicxulub asteroid, is what we believe was the impactor that collided with the Earth down in the Yucatan Peninsula and caused the dinosaurs to go extinct. So which one of these was more massive? Number 6, which one is larger, the International Space Station or the Arecibo Radio Telescope? And I'm just defining this as the end-to-end length of the space station and the diameter of the radio telescope. So not the total area of the dish. I'm not including these supports or the receiver up here, just the diameter of the dish versus the total length of the space station. Number 7, was more energy emitted by the explosion of supernova 1987A back in the year 1987, or by the sun over the entirety of the last century? So has the sun emitted more energy over the last 100 years than the single explosion of this supernova 30-ish years ago? Number 8, which is farther away? Polaris, that's our North Star, or the Pleiades, which is a cluster of young stars that we can see in the night sky. This is also known as the Seven Sisters. It's also the Subaru logo. Number 9, which is longer, or which is the greater distance? The distance from Earth to Vega, or Han Solo's Kessel Run shortcut? So this was famously, the Kessel Run shortcut was famously a distance, or quote, stated as if it were a time in the original Star Wars movie, even though it should have been a distance, and it was rectified later in the recent Han Solo standalone movie. But the exact distance was explicitly stated in the movie, so compare that distance to the distance from Earth to Vega. Number 10, which is colder, Arrokoth or the night side of Mercury? Arrokoth here, this is the Kuiper Belt object that was approached by the New Horizons spacecraft after it flew by Pluto back in 2015, 16, 4 or 5 years ago. After encountering Pluto, it then changed its trajectory and went and examined this very this very distant object at the edge of our solar system called Arrokoth. And I'm just asking whether this object's surface temperature is warmer or colder than the night side of Mercury. Number 11, would it take longer to drive straight upwards from the surface of the Earth to outer space, or to drive from State College to New York City? This is assuming there's no traffic, so just some perfect day or night when you can drive from State College to New York without getting slowed down or frustrated. And to drive straight upwards to space, I'm imagining that there's some imaginary road that goes straight up, allowing you to travel at some constant 60 miles per hour speed. And the boundary between our atmosphere and space is defined as something called the Kármán line, where the density just decreases enough that we've defined it to be a transition. Number 12, which one is older? The light that we observe from quasar 3C273, or the first appearance of life on Earth? So quasar 3C273 was the first quasar ever observed and discovered. And I'm asking here whether the light that we observed from this quasar is older. So that means, was it emitted before or after life first appeared on Earth? Number 13, which one moves faster or moved faster between Oumuamua? So this was the famous interstellar asteroid that passed through our solar system think it was 2 years ago, back in 2018, or Rama. And Rama was also a famous interstellar object that passed through our solar system in the famous Arthur C. Clarke novel, Rendezvous with Rama. And I'm asking whether this one's Oumuamua's peak speed through our solar system was faster or slower than the speed of Rama, as defined in the novel. Number 14, which one is larger, the original real Death Star or the fake Death Star, Mimas? Mimas is a moon of Saturn that has a famous crater feature on here that is reminiscent of what the Death Star looks like. And it's sometimes referred to by astronomers as the Death Star moon. And sorry, for larger here, I'm talking about mass. Which one is more massive? And last but not least, number 15, is there more alcohol in a pool full of Leinenkugel? A reference to our nice LSST drink today from Mixmaster Jacob. Is there more alcohol in a pool full of Leinenkugel or in the comet C2014Q2 Lovejoy? I'll be honest, I don't know how comets get their names, but that's what this one is called. And there was alcohol detected in it. So if that's a hint for anybody, I hope it helps. All right, I'm going to circle back to the beginning real quick. Let's see if I can scroll. Yeah, and I'll run through these real quick one more time. And then I'll pass it off to Jacob for astronomy in the news. And I didn't state this earlier, but the way this works is that we want you to all submit your answers to the trivia before Jacob finishes astronomy in the news. So I'm going to start grading right before the second talk begins, and I will not accept any more answers after that. And then, sorry, if this scrolls properly, there we go. And then we'll announce the winner of the trivia after the second talk is finished. So number one, which one is more massive, a Bok globule or gargantua from Interstellar? Number two, in outer space, are there more naked eye stars or Starlink satellites? Number three, have more people walked on the surface of the moon or served as NASA administrator? And I'm just going quickly because all the questions and options are in the trivia sheet, so you can just reference that if you need to. Number four, is it hotter on the surface of Venus or during spacecraft reentry on the spacecraft exterior? Number five, which one is more massive, Saturn's rings or the KPG asteroid? Number six, which one is larger, the International Space Station or the Arecibo Radio Telescope? Number seven, was more energy emitted by supernova in 1987A or by the sun over the last century? Number eight, which one's further away, Polaris or the Pleiades? Number nine, which one is larger, the distance to Vega or Han Solo's Kessel Run shortcut? Number 10, which one is colder, Arrokoth or the night side of Mercury? Number 10, would it take longer to drive straight upwards to space or drive from State College to New York City? Number 12, which one is older, the light emitted from quasar 3T273 or the first appearance of life on Earth? Number 13, which one moved faster, Oumuamua or Rama? 14, which one is larger, the original Death Star or the moon Mimas? And number 15, is there more alcohol in a pool full of Leinenkugel or the comet C2014Q2 Lovejoy? Okay, that's it for trivia. Submit your answers, come up with some creative names, and I will pass it over to our newscaster now.
All right, yep, Jacob, go ahead and tell us what is happening in astronomy today. Jacob, if you're talking, you are muted.
Good call. Good call. All right. So what you're looking at here, luckily I hadn't gotten that far into it. What you're looking at here is the largest digital photograph that's ever been taken. So this was released earlier this month by the Legacy Survey of Space and Time team, so LSST. So we're kind of tying it all back in here. And this picture contains 3.2 billion pixels, or 3,200 megapixels. This isn't a picture of space. This is actually the head of Romanesco broccoli, which is known for its very intricate detail and fractal nature. And this image is so large that it would take 380 4K Ultra HD TVs to display the full image. And so, as I mentioned earlier, with our drink, LSST is going to be conducted at the Vera Rubin Observatory in Chile, and is going to be capable of photographing the entire southern sky once every few days. And as I mentioned before, it's going to really pack a punch, generating about 20 terabytes of data per night. And in total, over the 10-year survey, is going to amass about 60 petabytes of data. So a lot of data to sift through there. But for now, we're just testing the detector on a picture of broccoli. Then in other news, earlier this month, there's a lot of talk about discovery of phosphine in the atmosphere of Venus. And so despite the fact that this is a toxic gas for organisms that like and enjoy oxygen, phosphine is produced on Earth a lot by bacteria and microbes. And on rocky planets, it's difficult to produce phosphine through abiotic routes. We've seen phosphine before in atmospheres of Jupiter and Saturn, but it's the extreme environments there that gives the extra energy necessary to produce it. So its presence on Venus could indicate past or present life on our closest neighbor. That said, we don't really know much about the complex chemistry and the conditions in Venus's atmosphere, so this is far from a secure detection of alien life or anything, and instead we'll just keep studying, propose for likely future missions to Venus to help understand this discovery and what it may mean. But it looks like Venus is back on the menu for space missions potentially, and I think this ties in very nicely with our next talk from Evan. So I'll hand it back to you, Michael. That's astronomy in the news.
All right. Nice time with the LSST and nice time with the Lord of the Rings reference. I got that.
Thanks.
All right. Up next, we have a talk from Evan Sneed. Evan recently graduated from Penn State as an undergraduate and is going to tell us about doing some research with looking at biosignatures and tech signatures in exoplanets, planets outside of our solar system, actually, which are on my back wall. Hey, planned that out well. All right, Evan, go ahead and take over.
Well, thank you for the introduction. And yes, those are wonderful posters. I love them. I saw them at JPL all the time. Everyone see the screen?
Yep.
Awesome.
Yes, you're good. You're good.
Awesome. Once again, my name is Evan Sneed. I am a recent graduate of the Penn State Astronomy program with a Bachelor's of Science in Astronomy and Astrophysics and a minor in Astrobiology. And today we're going to be talking a bit about biosignatures and how we're looking for life on other planets. So yes, we will end up talking about Venus. It wasn't my original plan for this talk when I was asked, but we will talk about Venus later on since it is pretty important recently. But first, we're going to talk a little bit about what biosignatures are, how we look for them, how we find them, some of my current research into biosignatures, then we'll talk about Venus, and then we'll talk about some non-atmospheric biosignatures, which I think are really fun, but they're kind of a new thing. So cloudy with a chance of ammonia, fun name. So once again, a little bit about me. I'm a postbac researcher in Professor Jim Casting's group over in geosciences, but I am a member of the astronomy department currently. I graduated this spring, and also I've done planetary chemistry research at NASA JPL. So this is something that I've been working on for the past 3 or 4 years over several different projects. So what is a biosignature? So biosignatures really are just any phenomenon that provides scientific evidence of past or present life. So as an astrobiologist, we ask these 4 questions really whenever we look for life on another planet or whenever we look for biosignatures. So what does life produce? Can dead planets fool us? how do we interpret limited data because we only have so much telescope time, and how do we quantify our certainties? So how sure are we that this is actually a sign of life? So the best, and this goes along with the best biosignatures are reliable. We know that they come directly from life themselves, or we can exclude the inorganic ways in which that biosignature is produced. They're readily available, so we can do multiple observations of them and make sure that it's not just a fluke, which we will also talk about later. And they're easily detectable. That definition is constantly changing, especially with the brand new telescopes and missions that we are launching. And obviously the idea of what a easily detectable biosignature has changed even over the past couple decades, and will continue to change. So we'll talk about what some of the brand new biosignatures that we think could be detectable are today. Just a little bit of jargon real quick that isn't super necessary, but I think is still useful if you are going to be looking into biosignatures, is this classification scheme. So there's Sarah Sager's group at MIT, which I will mention that name a lot today, introduced this classification scheme for biosignature types. So there's class 1, class 2, class 3, and then class 4. Class 1 are products from reduction oxidation reactions. Basically, these produce energy for an organism. So here I have the reaction for methane up in the upper left of this diagram. So that's going to be the reaction of methane within bacteria. You have byproducts for building biomass. So we have how you produce glucose, or I'm sorry, how you produce any sugar in a chloroplast. So that's also how you produce oxygen gas. That requires energy. You have products of secondary metabolisms, which is basically just about everything else. And that's in the bottom left. That is actually the reaction for isoprene, which is used by a lot of plant life and is a possible biosignature as well. And then we have bioindicators, otherwise known as type 4 biosignatures. And these are abiotic reactions with chemicals that are only made organically. So here we're going to say oxygen is a type 2 biosignature. So ozone, because it's only produced through oxygen, is a type 4 biosignature because because it relies on the use of oxygen. Type 1 and type 2 biosignatures, especially type 1 biosignatures, are the ones that are most likely to be falsified through inorganic methods. So methane, for example, we'll talk about, although it does have organic ways of being produced, it does get produced in inorganic methods also. Type 3 biosignatures, on the other hand, occur basically only from organic processes. However, they generally are found only in very small amounts in planetary atmospheres, and thus they're harder to detect. So when we're looking at these biosignatures, there's a lot of give and take about what are we going to be looking for and what concentrations are we going to be able to find them. So how do we find these biosignatures? Just like a lot of different things in astronomy, we use spectroscopy. So spectroscopy is the study of light and how light is absorbed and how it's emitted from different chemicals. So this is almost like we call it the spectral fingerprint of an element or a molecule. So different elements and different molecules give off different wavelengths of light when they are when light comes off from them or is absorbed by them. So, and we use this largely historically to study stars, figure out the composition of stars, how much hydrogen, how much metals are in the atmosphere of a star. But recently we've been able to do transmission spectroscopy by studying the host star of a planet and then seeing what light goes through the atmosphere of that planet. We can actually determine what the composition of a planetary atmosphere is. And that is super important and basically the grounds for everything that we're going to talk about today. Okay, so enough talking about how biosignatures work. Let's talk about some actual biosignatures. So oxygen and ozone are probably the simplest, most likely biosignature. The classic biosignature, everything on Earth that is complex life, except for some very, very, very rare circumstances that have only been found recently, rely on oxygen. There's a couple non-oxygen eukaryotes that don't use oxygen at all in their metabolisms that have been found within the past couple years, but in terms of eukaryotes, they're still pretty simple. So overall, complex life is going to require oxygen. And the rise of oxygen within Earth's atmosphere, it hasn't always existed in Earth's atmosphere. It's tied generally to the rise of eukaryotes and complex life, along with snowball Earth events a couple billion years ago in Earth's history. Before that, oxygen really was in the parts per billion range in Earth's atmosphere, and even earlier there was even less than that. What we have found is that oxygen actually is possibly going to be found even less, or it might be found more, but it might be found abiotically on planets, which is not something that we expected before the rise of exoplanets within our field. Finding larger planets and finding planets around M dwarfs, which are red dwarfs, smaller stars, much cooler than our sun. We've actually been able to discover methods in which we can produce oxygen abiotically. So oxygen really, a couple decades ago, was the classic biosignature and exactly what you wanted to look for when we were searching for life. But it's kind of fallen by the wayside. It's still important, but it's not the most important anymore. What we've really moved to now is a wide field, a wide approach rather than a narrow approach, and looking for many different biosignatures. The second most important biosignature in terms of Earth's history is methane. So methane is really the king biosignature before the rise of oxygen. It's an important part of the metabolism of mid-oceanic vent archaea, which are theorized to be some of the earliest life forms on Earth, and they still are happily chugging away today. If you go down to any mid-ocean vent now, you are going to find organic life that is completely different than what you're going to find at the surface. And it really speaks to what we could find for life on different planets. And it's theorized that this may be what we might find in the subsurface oceans of icy ocean worlds like Europa or Enceladus out in the outer solar system. So these are really important for looking at types of life that might not be just like us, although it likely will be something simpler. Methane also is a notable greenhouse gas. Right now, there's been talk about trying to limit methane. You may have heard of Congress talking about trying to reduce the amount of hamburgers people eat because cow farts basically help increase our global warming. That's something that has actually helped early Earth in the past to stay warm, even though the actual surface of the Earth might have been much cooler otherwise. Methane is also found in other parts of the solar system, especially on Mars and Titan. The Curiosity rovers found seasonal detection of methane in Mars's atmosphere that has been blamed for a multitude of different reasons. It's highly contested whether or not there actually have been found or if they're instrumental errors. Some people have said that they're not instrumental errors, but they're merely geologic reactions that we don't understand quite yet. And then even others have said that maybe this is signs of microbial life underneath in the subsurface of Mars. So maybe perhaps in those salty lakes that we found on that was just discussed by Arvind earlier, and that we found underneath the surface. Titan is probably the more well-known source of methane within our solar system, largely because of the organic haze that forms from methane. So this is, if you've ever been to a big city like LA or and basically just any big city, LA is the biggest for me, you're going to get smog that pales in comparison to this haze. This is why we ended up sending a probe to Titan, the Huygens probe from Cassini, to try to be able to peer through the haze of Titan and see what the surface is like. And now we're end up going back with the Dragonfly mission that John Hopkins is leading and Penn State has taken a part of, to go and see could this methane be organic? It's likely not, because this methane is found outside the methane ice line. So it probably is not organic. It's probably from an inorganic source, but Titan is still very interesting from other astrobiology reasons. Haze is going to be easier to detect with upcoming telescopes. Methane, sadly, has a lot of absorption lines that line up with water. So it's more difficult to detect. But once again, if we're looking for other types of life, this is going to be very important. Okay, about my research. So the discovery of super Earths and mini Neptunes and other types of planets that aren't found in our own solar system have completely changed the field. They have easier to detect spectral features due to lower atmospheric concentrations. Their atmospheres are much larger than like a nitrogen and oxygen-based atmosphere. And this leads to new possibilities for biosignature detections. I actually didn't have a good image for this. So unfortunately, you're going to get a picture of one of my posters. But ammonia is one of the things that has been hypothesized to exist on these planets. And it's kind of been my baby for the past year and a half. This was first hypothesized as a biosignature by Sarah Sager's group at MIT, and it's based upon how we form ammonia on Earth industrially for use in fertilizer and weapons and other fun things like that. So they suggest using a biocatalyst with hydrogen and nitrogen-based atmospheres in order to form ammonia. And that energy that is released from the breakdown of nitrogen gas can be used for anything you want related to life. We've actually found that this works very well, other than the fact that it's not very stable. So we're still looking into this, but this very much may be how we may find life unlike ours out there. It may look it may be based off of something like this. Another thing that was talked about by Sarah Sager's group is phosphine. Phosphine has been hypothesized as a biosignature for several years now, and we now know the reason for that is because of Venus has detected phosphine has been discovered in the atmosphere of Venus now over the past starting in 2018. So papers were formally published this year. This paper was produced earlier this year as kind of a theory paper by Sarah Sager's group. This was very interesting for a lot of us because phosphine is known to be on Earth very toxic and extremely flammable. It's so toxic that it's commonly used as an insecticide and as a rodenticide. And there are plenty of accidental deaths, human deaths, due to phosphine in industry and in laboratories. Because of that, phosphine is not something that is well understood in terms of simple molecules. We do know a lot about it, but in terms of some of the simpler molecules, phosphine is pH 3. Its chemistry is not fully understood. So this detection of phosphine in the cloud decks of Venus was almost an accident. So Sarah Sager's group was looking, they had published this theory that phosphine might be a useful biosignature. And so they were testing on Venus to see whether or not this was actually feasible to start going forward and looking for it in the atmospheres of exoplanets. And they actually found, much to everyone's surprise, a single detection of phosphine about 60 kilometers up in Venus's atmosphere. They've been unable to model its source so far, although much of it is still in review. There are several papers that are still in the review process, and we're looking at to try to see what is the source of this phosphine. They have put forward that a hypothesis that is formed by microbial life in Venus's atmosphere. So like I said, much of this is still in a review. Even about an hour ago, I checked arXiv, which is where we post a lot of our upcoming science articles. And a team at Cornell have already pushed out a paper to be able to try to explain this inorganically. So this is something that's going to be contentious for several years. So let's talk about Venus's atmosphere a little bit. So they found phosphine at 20 parts, that's 20 parts per billion, not 20 parts per million, that's a typo, at 56 kilometers up in the atmosphere. So Venus's troposphere is higher up than Earth's troposphere. So this cloud layer starts from about 50 kilometers and goes up to about 70 kilometers. So they found it around 60 kilometers. So just about the middle of this cloud layer. The surface of Venus is very dense, hot, and acidic, and it's in general, not a very nice place to be able to find life. And it's a lot of the reason why we have written off the idea of life on Venus. But the upper troposphere of Venus is a lot more Earth-like. It's got a pressure about the same as the surface pressure of Earth, same with the temperature. It's still pretty acidic, but it's something that is possible for life to be able to be found. So once again, they've hypothesized that microbial life could surf in the atmospheric currents and never touch the ground and completely find life in the atmosphere, just in the way that we have life in our atmosphere as well. So even if we took an agar plate right now on an airplane and we flew it through the clouds of Earth, we would actually find microbes as well. So is there a potential for life in Venus's atmosphere? Possibly. Interestingly, phosphorus was previously detected during probes that we sent to Venus, the USSR sent, and it was previously determined to be phosphorus anhydride. But those expect to start seeing reevaluations of that in the future. We may have possibly seen phosphine before and just previously misattributed it. We're still also looking at sources like Venusian volcanism and surface chemistry. The acidity of Venus leads to a lot of funky reactions. And phosphorus is just one of those chemicals that we still don't fully understand all of its cycles. So expect a lot of new interesting research, especially because now there's more interest in going back to Venus. We haven't sent anything to Venus in a while. We've sent some surveyors to orbit the planet, but MIT is now announced plans to send a weather balloon-like mission to survey the Venusian atmosphere. It's called the Venus Life Finder Mission Concept. And it may be a familiar name to some of you. It's funded by Russian billionaire Yuri Milner, which, if you are interested in SETI research, is the funder of Breakthrough Listen and Breakthrough Starshot, which is the plans to send a probe to Alpha Centauri. So this is really exciting for us, even if you don't believe that this is a biosignature and that there's life on Venus. But just our understanding our ability to understand more about our nearest neighbor, Venus, is something that we haven't been able to anticipate recently. Okay, the last part of this talk, I'm going to talk about non-atmospheric signatures. So happy fall, y'all. We're going to talk about pigmentation. So the reason that you see plants that are green, or right now they're more oranges or yellows or red, are because of pigments within those plants. And this is one of several different ways that vegetation mitigates heat. If you get too much heat, too much energy, you're going to burn out your plant cells and you're going to die. And so what evolution has really done to plants is make sure that they are stable over long periods of time instead of being the most efficient. So what we've done is, or what plants have done, even though the sun emits the most of its light actually in the green, plants have decided that they are going to reflect a lot of that green light. And so that's why most plants that you see are green. Now that it's towards the later end of the year, you're going to start seeing shifts to oranges and yellows. Those are some of the other pigments that plants have. But this reflection and absorption of different wavelengths of light is something that we find in basically all types of vegetation on Earth. And it's something that we could easily look for once we start having better telescopes, including the ability to do direct detections of the surfaces of exoplanets. So if we start seeing a large amount of one color, especially green or red or orange, it may be signs that there's something like plants there on the surface of the planet. There's also something called the vegetative red edge, which is used by our satellites today to peer onto Earth and look at how productive vegetation is on Earth, including crops. So light is reflected and refracted by plant cells, especially the infrared. That's why it's called the vegetative red edge. It's at the edge between the visible red part of the spectrum and the near infrared. So this is a image of South Florida by the Landsat 5 satellite in false color. So the color green here is represented by this kind of dark blue you've seen here on the tip. This is a lot of algae that's grown largely from fertilizers that's leached into the ocean. This near infrared is this kind of lime green that's shown at the bottom in the Everglades, and up top in this very in some of the agricultural regions south of Lake Okeechobee. And the mid IR is red, which we see in some of the more barren fields of the agricultural district, and then we can kind of see it in some of the clouds as well. So we can also use this method to peer at the spectra of exoplanets to be able to determine whether or not there's vegetation there. One of my more favorite ways, and one of my last slides, is to talk about biofluorescence. So this group at Cornell has talked about ways that other types of life might be able to reflect excess heat, to get rid of excess heat, and that's through biofluorescence. So if you've ever taken a black light to like highlighter, or I don't know, some of those like funky indoor golf courses, this is what you're going to see. So photosynthesizers are the major source of biofluorescence on Earth, but here we see some coral. Other types of some animals also do it, and including minerals. So this is hypothesized to be an efficient way to get rid of excess energy around planets with large ultraviolet fluxes like M stars and F stars. Finally, just real quick, I want to talk about technosignatures. Penn State has really started to embrace this. We've started the Penn State Search for Extraterrestrial Intelligence Center. We've moved past just looking for technosignatures in the radio. We're also looking for heat mitigation strategies, just like I talked about for plants before, but we're looking on larger terms, like Dyson spheres. And we're also looking for more traditional biosignatures. So things like phosphine, which could also be which is also produced by industry, or ammonia, which is also produced by industry. We may find things that could be produced organically, but also could be produced solely through industry, such as like chlorofluorocarbons. So we're starting to do a lot with that here at Penn State, and I'm super excited to be a part of that work. And finally, we also have the Center for Exoplanets and Habitable Worlds here, which is the main umbrella organization that works for all of this. It's an incredible team at Penn State over several different departments that work towards this. And if you're interested in learning any more about this, looking at both the PSETI and the CEHW websites, those are incredibly useful. There's going to be a lot of upcoming technology that will make this search for life a lot more interesting. It's already incredibly interesting, but I'm super excited to see what the next couple decades will bring us. And maybe we'll find something out there in the next couple decades. It would definitely make an interesting career for me. A little bit over time, but I wanted to say thank you. And if you have any questions, type in the chat. Thank you.
All right, thank you very much, Evan. And yes, if anybody in the chat, if you have questions for Evan, please go ahead and type them there in the chat. We can go ahead and ask them. So of course, have we discovered aliens yet? Yes or no?
Probably not.
Probably not. Okay. Okay.
Like I said, there's still so much that's under review. And we don't know a lot about Venus's atmosphere still. And the chemistry of Venus's atmosphere. There's still a lot that there's still a lot that is unaccounted for. One of the things I didn't show is from this Nature paper that was released that shows the proposed atmospheric chemistry for forming phosphine, and about half the reactions are still not fully accounted for. So there's still a lot of wiggle room and the possibility that this could be something other than microbes within Venus's atmosphere. And even if it is, maybe it's something that Earth life traveled to Venus some way, maybe through an asteroid or something like that. So maybe we're actually finding Earth life just on another planet. So either way, no matter what happens, it's going to be incredibly interesting. But no little green men.
All right, and the word, like, if you're taking life and like hitting it with an asteroid and the asteroid carries it over, the term for that, I guess, is lithopanspermia, which is like one of my favorite words that I've learned in astronomy. So you all know something new today, lithopanspermia. Okay, so kind of building off on that, I guess, let's say 2040. Do you think that we will find evidence of life on a planet, either in our solar system or outside of our solar system, before 2040? So just a very speculative question. What is your opinion? What is your opinion on that?
Are we going to find signs of life? Oh, yes, we're going to find signs of life. Are we going to be able to fully say 100% that this is life? I don't know so much about that.
Okay.
We are looking at sending missions to the outer planets as we speak. I talked a little bit about the Dragonfly mission to Titan. I'm incredibly excited for what we're going to learn. We're going to use a drone, just like some of the quadcopter designs that you see on Earth now. We're just going to supersize that, bring it up to the size of a car, and we're going to fly it around on Titan. And we're going to take a bunch of samples of the atmosphere and of the surface. And we're looking at things like Europa Clipper. So all these different missions that we're sending out to the outer parts of the solar system are going to bring brand new discoveries with them that I think are going to really change the way that we understand life. And of course, our explorations of Mars are bringing new things yearly. I mean, take today's press release. So we keep on finding more and more things about Mars. And even if we don't find signs of life that are still there right now, there's still a lot that we can learn about Mars's past and Venus's past that may suggest that they might have once had life on them.
Do you expect to find biosignatures or text signatures first? I guess if you're looking at exoplanets, not like stuff in our solar system.
If we're looking at exoplanets, well, technosignatures have been looked for a while. So, there's something to be said about, we haven't found much yet. But we also have not explored the full range yet. Recent calculations have shown that the sample size that we've looked at in terms of technosignatures is something akin to a bathtub worth of water compared to the entire amount of ocean water on Earth. It's just a cosmically small amount of the parameter space that we've looked at. So while a bunch of people are not super optimistic about SETI, I'm and looking for technosignatures, I'm a little bit more optimistic that we still have not found it yet, and that we may find it, or maybe perhaps it'll find us. So that's my guess, but and technosignatures are biosignatures to an extent, so I guess that's an easy cop out of that question also.
Fair enough. Okay, so a question from the chat. Which planet or body in our solar system do you think is most likely to have life other than Earth?
Ooh. Well, yeah, Earth would be the easy one. I'm going to go for Europa personally. At JPL, I was part of the team that worked on looking for life underneath these icy ocean worlds. Our understanding of Europa's subsurface oceans and the tectonic activity that occurs underneath really rivals what we find in mid-oceanic ridges on Earth. From what we understand, they're almost identical, other than the size of the planets, or in this case, the moons. Europa is the largest of these, of the two, Europa and Enceladus. Titan is also really interesting, although I'm not so sure whether or not we'll find it there first. So personally, I'm a fan of Europa, but I will be happy if we find it anywhere.
Fair enough. And you mentioned that we found these methane signals on Mars. Do you know if the Mars 2020 mission, I guess it's now Mars Perseverance, if that mission is going to be searching for methane as well?
I believe it's going to be looking for it within the crater itself. So it's going to be within Jezero crater, I believe. We might not be able to find signs of it itself. Previous looks into methane on Mars have really depended on the seasons of Mars and the wind. So we've been able to track how the current air currents on Mars work to some ability. And so we're still not sure exactly where the source of methane is, and it does appear that it might be somewhat related to the wind patterns, although that's still very tentative. So there's a possibility that we might discover it. We might see it with Perseverance, but I'm not going to place my bets.
Okay. Kind of going back to an earlier question, you mentioned the Dragonfly mission, like Dragonfly mission, Europa Clipper mission. What stage are those missions in? Like, are they fully funded? Are they actually building the things right now? How close are they to being launched and being sent out to their planets?
So both of those missions have been fully funded and are currently being built. Europa Clipper is, if I remember correctly, it's about halfway done. So that's being led by the team out at NASA JPL. They're still building it, and for a while, there was talk about building a secondary component called Europa Lander. That was, last I know, was scrapped, although there's still a lot of talk about bringing it back in various different multitudes. So the idea would be Lander would go, or Clipper would go surface and map the surface of Europa, and then Lander would use that findings to go and land on the surface, drill, take samples, etc.
Yeah, that's what we want to do, right? We want to see what's underneath that, what's in that
Exactly.
ocean. Like that's you gotta get to that ocean. But
Unfortunately, a couple kilometers of ice is a little difficult to get through.
it's true.
Dragonfly is a little newer in terms of being approved. So it wasn't announced to be approved, let's see, last June. If you're interested, somewhere on the internet, I actually did a talk about that for last year's Astrofest. So somewhere on the internet, I'm sure you can find it. If not, message me on Twitter or something. That's being led currently by the team at Johns Hopkins Applied Physics Lab. That I believe is going to be tentatively launched in the mid 2030s. So it'll get there. It'll get to Titan probably in the 2040s.
Okay. And so then I guess going back to Venus, like, this is a really recent discovery. Maybe you want to go there. We want to go to Venus now that we know this, but you got years that it has to take to build the thing, to propose for it, to get accepted. Are there missions existing now that I guess are in the works to go to Venus in the next, like, say, 10 years or so?
Well, if you want to go really short, right now we have a mission to Mercury. It's by the European Space Agency called Bepi-Colombo. And Mercury is really interesting as a planet. Maybe not in terms of astrobiology reasons, but Mercury is really interesting just because it's the closest planet to the sun. So that's why some space agencies are really interested in visiting, and why we've sent this, why we're sending this craft there now. It just so happens that in a couple weeks, Bepi-Colombo will be passing right past Venus. So there's still talks to see whether or not we can actually wake up Bepi-Colombo in time and get it situated so that it can try to observe Venus while it passes. If not, the way Bepi-Colombo's orbit works, it does some fun orbital dynamics to try to get into orbital insertion around Mercury. So it will pass back around Venus in about a year, and so that's probably more likely that Bepi-Colombo will be able to observe it. Now, the other thing that's important about this is that since the MIT group that is leading this mission to Venus, it's not, as of right now, it's not being funded by any sort of space agency. It's being funded by our good friend, Russian billionaire Yuri Milner. So we don't have some of that legislative loopholes that we have to wait through that, it's kind of chronic nowadays. Cough, cough, SLS, JDOST, et cetera, et cetera. So, maybe we will get something, it's a fairly simple design. It's basically a big weather balloon. We've done that. Getting something there, it'll still take a couple years to build, but as of right now, I see no reason why we couldn't get it there by the end of the decade.
All right, that would be pretty amazing.
Yeah, anything we can learn about Venus.
Yeah, Venus has kind of been, I feel, the neglected child of the solar system. People kind of put off Venus. So yay for Venus, it's coming back. It's making a resurgence. All right, thank you, Evan. Thank you for coming out here, giving a talk. Really appreciate it. Thanks again.
No problem. Thank you.
All right. We are ready to find out our trivia answers. So Arvind Gupta, come online. I'll hand it off to you and tell us who won trivia and what the answers were.
Cool. All right, I'm sharing my screen now. So great talk, Evan. I admire and envy your optimism that we'll find life soon. I wish I were that confident in that. Yeah. So, all right. So the trivia answers, I'll go through these kind of quick since we're running a bit slow tonight. Number one, which is more massive, a Bach globule or gargantua from Interstellar? Turns out Bach globules are at most something like a few dozen times the mass of the sun, maybe 50 solar masses. Gargantua was at a minimum 100 times the mass of the sun, according to Kip Thorne, who was one of the scientists that was consulted in the making of that film. So Gargantua was the more massive object in this case. Number two, in the sky, are there more naked eye stars or star-linked satellites? Naked eye stars, it depends on how exactly you define it, but it's something between 6,000 and 10,000. Starlink satellites, I think there are actually just under 1,000 up right now. So the correct answer is naked eye stars. But in the next decade, unless we can get some better regulations, there will eventually be more than 12,000 Starlink satellites in the sky. Number three, have more people walked on the moon or served as the administrator of NASA? If this question were asked 10 years ago, the correct answer would have been more people have walked on the moon, because 12 people have walked on the moon, and Jim Bridenstine, the current NASA administrator, is the 13th administrator. So this one just edged out the number of people that walked on the moon. Number four, is it hotter on the surface of Venus or the exterior of a spacecraft during reentry? The surface of Venus is something like 700 Kelvin, but spacecraft can get up to 1500 Kelvin, usually somewhere over 1000 Kelvin during reentry. So the correct answer is the spacecraft. Number five, it turns out Saturn's rings are something like 10 to the 19th kilograms, whereas upper limits on estimates of the mass of the KPG impactor are 10 to the 17th kilograms. So Saturn's rings are about 100 times more massive at the low end than the asteroid. Number six, which one is larger, the ISS or the Arecibo radio telescope? The Arecibo telescope is larger by a factor of 2 or 3. I don't know the numbers off the top of my head, but this dish is enormous. It was built in a natural, not exactly a crater, but a natural valley down in Puerto Rico. Yeah, it's huge. Number seven, was more energy emitted by supernova 1987A or by the sun over the last century? This is supernova 1987A, and it's not even close. Supernovae like this emit something like 10 to the 51 ergs, and over its entire life to date, the sun has not yet emitted that much energy. So the last century would be way too much of a low ball. By the time the sun dies, it probably will have exceeded the supernova, but for now, it's not even close. Number eight, which one is further away, Polaris or the Pleiades? So this one, I gave credit for either answer. I actually found out while I was looking up this question just to make sure I knew exactly what I was doing. Polaris is, the distance to Polaris is a little bit controversial actually. Based on some methods and measurements, it's about 450 to 500 light years away. Based on others, it's only 350 light years away. And the Pleiades are roughly 450 light years away. So depending on which methods you trust, your answer could be one or the other. So I gave credit to everybody that answered either of these. And I promise that did not affect the final results. Number nine, which one is longer, the distance from Earth to Vega or Han Solo's Kessel Run shortcut? Vega is just under 8 parsecs away. And as Han Solo famously claimed, he completed the Kessel Run in less than 12 parsecs. So you could argue that less than 12 could also be less than 8, but Chewbacca clarified that it was actually closer to 13 and Han Solo was lying. So the Kessel Run shortcut was longer than the distance to Vega. Number 10, which one is colder, Arakoth or the night side of Mercury? So Arakoth is very, very far away from the sun. It does not get much irradiation, and its surface temperature is, it's a little bit uncertain, right, because we didn't have a great measurement, but it's somewhere between 30 and 60 Kelvin. The night side of Mercury is really cold because it's in a spin orbit resonance with the sun. So one side of the planet is more often facing the sun than the other side. But the night side doesn't actually get as cold as Arakoth. It only gets as cold as about 100 Kelvin. So Arakoth is the correct answer here. Number 11, would it take longer to drive straight up to space or to drive from State College to New York City? The Kármán line, that definition I talked about earlier, is about 100 kilometers up, or 60 miles. So if you're driving 60 miles an hour, it would take 1 hour. State College to New York City is about 3.5 hours, as is State College to pretty much anywhere you would want to go. So the correct answer would be driving from State College to NYC. Number 12, which one is older, the light from quasar 3C273 or the first appearance of life on Earth? This quasar is actually only, and I say only just because many quasars are further away, it's only 2.4 billion light years away, which means the light coming from it is 2.4 billion years old. Life on Earth evolved much more than 2.4 billion years ago. We actually started having oxygen production and aerobic respiration 2.4 billion years ago. So life on Earth is older than this quasar. And something that might have clued you in was that this was the first quasar we discovered, so it's pretty close to Earth relative to other more distant quasars. Oh yeah, and there's only one person that got this correct, so good on you. Number 13, which one moved faster, Oumuamua or Rama? So Oumuamua at peak speed through the solar system was just under 100 kilometers per hour, whereas Rama was actually traveling through the solar system at 100,000 kilometers per hour, which is really fast and actually makes it incredibly impressive that they managed to rendezvous with it, as they state in the title. Number 14, which one is larger, the original Death Star or Mimas, the moon that looks like the Death Star? Mimas is actually a little over twice as large as the original Death Star. And I had to consult my housemate on this one because he knows way more about Star Wars than I do. I put original in parentheses here because the Death Star 2, or the second Death Star, would have actually been significantly larger than Mimas. So I had to clarify that here. And number 15. So a pool full of Leinenkugel has obviously a significant amount of alcohol, but not even close to as much as there would be in a comet. And for reference, there was ethanol detected in the outgassing from this comet here from Lovejoy. Ethanol is also known as drinking alcohol, and that's how I made the comparison. So the correct answer here is Comet Lovejoy. So if you are short on alcohol and need some more, you might want to catch a ride on the comet. So these are the prizes. Our winner tonight was Requizzi. So congratulations, you got 12 out of 15 correct, more than anybody else. And an honorable mention, this was the second place person who got 10 out of 15, had a great team name, which was No Creativity Today, sorry. So I will send an email out to you, Requizzi, and let you know about your prizes. So thank you. I will cut the share here and pass it back to Michael.
All right, thank you, Arvind. Surprised that you referenced Solo. I kind of thought as a society we had decided to ignore that movie altogether, kind of like the last Airbender movie, which was never actually made. Well, thank you everyone for coming out. Thank you, my co-hosts here, Arvind and Jacob. Thank you, Corey and Evan, for giving amazing talks tonight. We will be back again next month, late October, with some spooky astronomy. So please stay tuned to our Facebook page, our Twitter, our YouTube channel. I feel I have to say like and subscribe. I don't like saying that, but if you are interested, please do follow our YouTube channel. You can find out more about us. So thank you everyone for coming out, and we will see you in about 1 month. Thanks.